pour
sound a word of
augmenter la résistance
caution
du béton.
that this may not
Cependant, je voudrais
always be the
lancer un
case,
avertissement, ça n'est pas
because
toujours
I
le
have
cas.
found
J'ai
cases
trouvé également
in
des
which
cas
ACC
où
decrease
le durcissement du béton
the
diminue
compressive strength, or in general, the mechanical strength
la
of
résistance
mortar and concrete
à la
samples.
compression ou en
And the
général à la
reason is
résistance
that
mécanique
the
des échantillons
formation
de
of
mortier
calcium
béton.
carbonate
Et la raison est que la formation
may
de
have occurred at the
carbonate de
expense
calcium
of calcium silicate hydrate,
peut avoir
which we all
lieu
know
au
is the
détriment de
glue that
l'hydrate de
holds
silicate
all
de
the
calcium,
particles in
qui, nous le savons
concrete
tous, est la
together.
colle qui maintient toutes les particules du béton ensemble.
Over here, I would like to share with
Je
you
voudrais
some of the
partager
latest
les derniers
results
résultats d'une étude
from a study from
menée par
an international colleague of
un
mine,
de mes collègues
in
internationaux,
which they compare the mechanical
dans
strength
laquelle il
of
compare
motor
la
mix
résistance
with
mécanique d'un
and
mélange
without
moteur
ACC. So
avec ou
just like
sans
what I've
ACC.
mentioned a while ago,
Donc, comme je l'ai
this is
mentionné
a
il y a un
study that
moment, c'est
shows
une
that
étude
with
qui montre
ACC,
qu'avec
the mechanical
l'ACC,
strength of
la
motor
résistance mécanique
can be
du moteur
increased.
peut être
So this is
augmentée.
one of those few
Il
articles,
s'agit donc de ces
maybe
rares
less than
articles,
20 so
peut-être
far,
il y en a
that
moins de
shows this
de
great
20 jusqu'à
potential
aujourd'hui,
of
qui montrent le
motor
grand potentiel
using ACC
de
as a
l'utilisation
mean
de
of reducing
l'ACC
carbon in the first
comme un
place,
moyen de
and of
réduire
course,
le carbone en
in
premier lieu,
another, to
et
increase the strength.
deuxièmement d'augmenter
But
la
once
force.
again, I would like to reiterate that this
Encore une fois, j'aimerais
increase in
rappeler que cette
strength may not
augmentation
be
de
universal,
résistance
and
n'est
therefore we
pas
need to
forcément
be very
universelle et que
careful
nous devons donc être très
in
prudents
our assessment
dans
as well
notre
as
évaluation ainsi que
implementation
dans la mise en
of
œuvre
ACC,
de l'ACC,
especially if we are interested to
en
implement
particulier
ACC
si nous
over a
souhaitons
large scale.
la mettre à l'œuvre à grande échelle.
Let us continue.
On peut
Point
donc
4,
continuer.
if biochar is able to increase the strength
Point
of,
4, si
for
le
example,
biochar est capable
concrete,
d'augmenter la résistance, par
as
exemple du
shown over
béton,
here,
comme indiqué,
is there a possibility
montré ici, y a-t-il une
that we can
possibilité
then design smaller or thinner concrete component? I
de
think that is a
concevoir des
good
éléments de
question.
béton plus
All right.
petits
So
ou plus
this
minces?
is
Je
one of
pense
the
que c'est une
future
très bonne
direction of
question. C'est
research
l'une des
of
futures directions de recherche
my group in
de mon groupe.
NUS. And if we can indeed establish that we can reduce
Si
the
nous
size
pouvons
of
effectivement
concrete,
établir
then
le fait que nous
the
pouvons réduire
addition
la
of
taille du
biochar
béton,
would have
alors
another way
l'ajout
of
de biochar
reducing
serait un
carbon
autre
emission.
moyen de
Point
réduire
5,
les émissions de
reduction in
carbone.
CO2 emission
Point, la
can
réduction
also
des
be
émissions de CO2 peut
realized
également
by using
être
recycled
réalisée
materials. For
en
example, the
utilisant des
use of
matériaux
recycled
recyclés.
plastic in
Par exemple,
concrete or
l'utilisation de
any
plastique
kind
recyclé
of
dans le
composite
béton
medium.
ou tout
For
type de
concrete,
matériaux composites pour le
in
béton.
point 6, further reduction in CO2
Une
emission
réduction
can also be done by
supplémentaire
the use of
des
pozzolanic
émissions de CO2 peut également être réalisée
admixtures,
par
and this can be
l'utilisation de
used to replace parts of
pozzolanic.
cement.
Et
Or we
cela peut
can
être
also do
utilisé pour
so
remplacer une partie
by
du ciment.
using
Nous pouvons
recycled
également le
aggregates. For
faire en
example,
utilisant des agrégats
partially
recyclés.
replacing or
Par exemple,
even
en remplaçant
entirely
partiellement ou même
replacing sand and gravel
entièrement le
with
sable et le
other
gravier
recycled
par
material.
d'autres matériaux recyclés.
This slide
Cette
shows some of
diapositive
the commonly used
montre
alternate aggregates for greener concrete. And in
certains des agrégats
particular, in
alternatifs qui sont
Singapore,
utilisés
we make
pour un béton plus
use of
écologique.
what
En
we call
particulier à Singapour, nous utilisons
RCA,
ce que nous appelons
recycled concrete aggregates. And
nos
basically, these are
agrégats de béton
gravels,
recyclé.
the
Il s'agit
coarse
essentiellement
aggregates
de gravier,
that
de
are salvaged
granulats
from old
qui
concrete
sont récupérés des autres
for
bétons
constructing
pour
new
construire
concrete elements for new
de
buildings.
nouveaux
Right. And of course,
bétons pour de nouveaux bâtiments.
if we are interested
Bien
to
sûr,
make use of food waste in
nous
or as
sommes
a
intéressés
construction
par
material
l'utilisation
in
des
new
déchets
buildings,
alimentaires
then
comme
I
matériaux de
think
construction dans les nouveaux
one
bâtiments.
way of doing so
Je
is by
pense que l'une des
converting
manières de le
that into
faire est
biochar and
de
then
les
deploying the
convertir en
biochar
biochar, puis
into
ensuite
either
de les déployer
composites or
dans les
concrete.
composites ou le béton.
So in conclusion,
Donc pour conclure,
there are 3 points that I would like to
je
emphasize.
voudrais insister sur 3 points.
The first is that
principalement.
renewable energy
Le premier
continues to
est le
play
fait
a
que les énergies
crucial role in
renouvelables
achieving
continuent
carbon
de
neutrality
jouer un
and
rôle
net
crucial
zero carbon.
dans la réalisation de la
However,
neutralité carbone
whether
et
something,
atteindre le zéro
for
net carbone.
example,
Cependant,
biochar concrete, is
pour
carbon
déterminer
neutral
si un
or
produit,
even,
par exemple le
hopefully,
biochar
net
ou le
zero
béton, est
carbon
neutre carbone,
or not, should be based
il
on our
faut se
assessment of
baser
life
sur
cycle and embodied carbon.
notre
So this
évaluation du
is
cycle de
very
vie
important so that we can be
carbone.
as
C'est très important
holistic
pour que
and,
nous puissions être aussi holistiques et
in our
complets
assessment
que
as
possible dans
possible.
notre évaluation.
And finally,
Enfin,
achieving carbon
pour atteindre
neutrality
la
requires a
neutralité
multi-pronged
carbone,
approach. And when
cela
used
nécessite
as a
une approche à
component
plusieurs
in building
volets.
materials, we have shown that biochar can
Et
contribute anywhere between
nous avons
10
montré que le
to
biochar
30% of the
peut
total
contribuer à
carbon
10
reduction.
30% de la réduction totale du carbone.
And at this note, I would like to
À ce
acknowledge
stade,
and thank
je tiens à
NRF
remercier
and our Ministry of Education for providing
NRF et
the
notre
funding
ministère de
for my
l'Éducation
different
d'avoir
projects so
financé les
far.
différents projets
And
jusqu'ici.
of course,
Et
we
bien
have
sûr,
put forth 2 new journals,
nous
academic
avons
journals
publié
that
2 nouvelles
accept
revues
articles on
académiques
biochar
qui acceptent
and
des articles sur le
more
biochar et plus
generally
généralement
different types of
différents
carbon
types de carbone.
reduction technology and strategies. So if any one of
Différentes
you,
technologies ou
after listening
stratégies.
to
Donc,
this, is
si
interested to know
après avoir
more
entendu
about any
cela,
of these
vous êtes intéressé à en savoir plus sur l'un de
journals,
ces journaux,
please
ces
feel
revues,
free to speak to
n'hésitez
me.
pas à m'en
And I
parler
can be
et
contacted
je peux vous
through this
contacter
email. So at this point,
via
I would
cet
like to
email.
thank all of
Je
you
voudrais maintenant vous
for your
remercier
kind
pour votre
attention.
attention.
I'll be available to
Je
answer any
suis à
of
votre
your
disposition pour
questions
répondre à toutes vos
regarding
questions
any part of this talk.
concernant
Thank you very much.
n'importe quelle partie de cet exposé. Merci beaucoup.
Oui, alors c'était prévu une petite session des questions-réponses.
We
mais on n'arrive
were
pas à voir
supposed to
l'intervenant, donc
welcome
peut-être on va se connecter
a
tout à l'heure, on verra.
Q&A
Donc, on
session,
est
but
obligé de
we
passer
can't
au
seem to
à la
connect
prochaine
with our
intervenant. Donc,
presenters. So I
j'invite
must unfortunately
Michael,
continue
Michael,
on with
avec toutes ces
the
langues,
program. So I would
Brogle,
like to now welcome
de nous
Michael
rejoindre
Brogle,
pour parler de la
Business
vision de
Development Manager
Neustark
of
de
Neustark,
Suisse.
who's going to speak to us about the
Et la
Neustark
thématique, c'est
vision.
comment stocker durablement les CO2 biogéniques dans les
The
bétons.
title
Je
will
lui laisse la
be
parole.
the permanent storage of CO2 in recycled bitumen.
Okay, hello everybody. My name is Michael from the company Neustark. We
Bonjour
are
à
a
tous.
startup based in Switzerland. So we're about for 3 years on the market, and the technology I'm going to present to you is at the stage that it is commercialized in Switzerland, and we are entering new markets right now. So basically what we are doing, we are permanently storing CO2 in recycled concrete. Need to quickly check how can I move the slides? The white one? Oh, okay. All technical issues solved. Okay, so basically, in general, we are in the carbon dioxide removal sphere. basically, I think which you know very well, with every ton CO2 that was emitted or is emitted, we have the aim to store 1 ton of CO2 to receive basically in the end a net zero world. We are active in the concrete industry. As you might know, the concrete industry globally is one of the largest emitters. So 7% of all the concrete 7% of all the CO2 emissions worldwide comes from the concrete industry. When we look at why this is basically, as we saw in the presentation before, because of the high temperatures that are needed to get cement, as well as the CO2 that is emitted during the cement. What we are trying to do is basically, we're not looking at the production of cement itself, but we take the possibility of old cement that can be found in recycled concrete and then has the uptake potential for CO2 and can basically store it permanently. What you see here is a typical recycled concrete granulate. So when they come from the construction site, they come in different sizes, and they are broken down in different dimensions again, so they can be sorted all the way down to the sand and gravel. The business model Neustark uses is basically a seamless integration of the existing value chain of concrete recyclers. Basically, what you see here on the left side is the demolished concrete that comes from the construction site and is brought to concrete recycling plants. So these are all existing institutions or existing businesses that take place today. At the concrete recycling plants, the recycled concrete is crushed into granulates, and then it is further utilized either to put into ROTHs as recycled aggregates, or it is used to build fresh recycled concrete. Now, where we come into place is basically we produce machines which can be used at the concrete recycle plant, where the recycled concrete can be placed into the installation, and we inject biogenic CO2 over the course of 2 hours up to 12 hours. And we close that the bunker basically for this time being of the injection. And what happens is that the gravel or the recycled concrete aggregate during this time takes the CO2 and permanently binds it back into limestone again. In order to basically provide the CO2 to the recycling concrete producers, we have to build up the complete value chain. Basically, we need to have biogenic CO2. That's something we do as well. So we go directly to biogas plants and we purchase the CO2 either in a fluid or in a gas form. We then make sure that it is liquefied at the biogas plant. We transport it to the concrete recycler, where it's then being stored. And in order to make the complete business model functionable, we in the end sell the CO2 certificates on the voluntary carbon market, which then again allows us to reimburse the concrete recyclers with a certain amount. We have to understand that the concrete business is a low margin business with a very high volume. So typically, if you would like to upsell or if you would like to upcharge recycled concrete that has been carbonated to put into ROTHs, typically nobody will pay you the extra margin for that. Therefore, what we are doing is we are providing the concrete recyclers with a functional business model that they basically getting reimbursed for every ton of CO2 that they have stored in their recycled concrete. Here are a couple of pictures on how this really looks like. So this is from the source side, basically. This is the biogas plant in Switzerland, where what you see here is the orange container. That's a liquefaction plant. The good thing is that the CO2 that we can be of low quality. So we always say that concrete aggregate basically doesn't really have a demand on what kind of CO2 this is. Hence, we don't have to invest in very highly engineered liquefaction plants. So we can use basically all kind of CO2 that comes out directly from the biogas plant. We are then transporting this to the construction site, to the recycling plants. What you see here are a few different solutions that we use. Basically, the orange containers you see on the large pictures are some of the mobile containers. They function nothing else than you open the lid, you enter the gravel or the recycled granulates with the wheel loader, you close the lid, you inject carbon for 2 hours, and then basically you bring the concrete back, the recycled granulates back into the value chain. You see a couple more on the right side. These are more the fixed installations. Basically, when you go to concrete recycling plants, what you always find are silos where the recycled concrete granulates are stored, because what they do is they bring it either back into their process to create concrete, or they bring it out to the roads. So there's always already a storage unit around. So what we do is we make sure that storage unit is airtight, and we we add an injection system, and basically that's it. So it's quite simple to do it. All it needs a very good process at the concrete recycling stations in order to guarantee that their process is as efficient as it has been before. This here is a graph of the CO2 uptake. Basically, it depends a little bit on the amount of material that is being carbonated. But what we see is typically after 12 hours, the uptake potential of the concrete gravel is achieved. So it doesn't really matter if you carbonate it longer. So if you have sort of smaller bunkers, it will be fine if you carbonate for 2 hours. If you have larger bunkers, often this is done overnight. So the bunkers are closed overnight. The carbon is injected in the morning. The concrete recyclers take out the carbonated gravels, and they go back into their process. On the right-hand side, you basically see the surface before and after the treatment. What you see is that all the little the surface basically that you find within the sand or the gravel is being filled with CO2. Basically, in other words, it's limestone again. If we look at the complete process that we are doing, you will find that we have a 93% removal efficiency, meaning with every 1,000 kilograms of CO2 that is permanently stored, or with every 1,000 kilograms of CO2 that is stored, 930 kilograms are effectively stored. So in other words, 70 kilograms are 70 kilograms of CO2 are being used in the process. So that's the gray emissions. Basically 30% or 30 kilograms is used to liquefy the CO2. So that's basically the largest emission within the process. And then we have some parts of the concrete, and then a minor part is the mineralization. So in total, when we go to the market on the voluntary carbon market, for every we have a net balance. We can sell with every ton CO2 stored, we can sell 930 kilograms on the voluntary carbon market, which is quite an efficient process actually. Here are two examples of companies that we work with on the voluntary carbon market. For example, UBS, a Swiss bank, as well as Microsoft. As you might know, Microsoft is one of the largest buyers currently in the voluntary carbon market. And they are definitely doing a very, very good job to help scale that market, and help us as well to bring our business model into place. So generally, where are we active? The orange dots, these are the sink projects, so all the carbon recycling plants, and the black dots are the source projects, so all the biogas plants. For this year in Switzerland, we currently have 3 biogas plants running, or we are in cooperation with three biogas plants, as well as we have roughly about 7 sink projects, and we aim to have 2 to 3 biogas plants more, as well as roughly about 15 plants in the market. And in addition, we plan to enter the European market. Basically, what we've done last year is that we have proven the business model up to the commercialization. We could hand out the first paybacks to the concrete recyclers, and we are confident that we can now move into other European markets such as Germany, Austria, France, and the Netherlands to really scale to the point that our goal is basically by 2030 that we can store 1 million ton of CO2 through the concrete recycling plants. Wonderful. Thank you very much. Are there any questions?
Hello, thank you very much for your presentation. I have a question concerning the CO2 as gas form. If it is used directly to feed your system, which pressure is required for your system? Which pressure containing the CO2 in gas form to feed your system?
You mean to feed the system on the sink side?
Yeah.
I would have to quickly check afterwards what the exact pressure is. So basically what we do, we install the so when we're at the recycling plants, there's 2 systems needed. One is the storage for the aggregates, and the other one is basically everything that goes around the CO2, so make it liquid again and build up the pressure. What the exact pressure is, I can tell you right afterwards.
2 quick questions. One, you mentioned the 7% to start with. Is that including what's being carbonized in concrete, or is it like the emissions?
So the 7% is really the emission. It's really the worldwide emissions of the concrete industry, coming from the energy that is used to produce cement, and the CO2 that goes out into the air when you basically heat up limestone.
So the exact number post-production could be much lower than that?
Could be much lower, exactly. But we do not try to include our methodology to mix up with producing fresh concrete, because it's really basically 2 sides. So one is really producing fresh concrete, and where we come into play is we use the uptake potential of the recycled concrete. That, of course, if you use that granulate and you build again with recycled concrete, you need less amount of fresh concrete. But we don't really want to make a complete calculation for the concrete industry. What we want to show is that the recycled concrete has a massive uptake potential of CO2, and that alone helps to store a lot of CO2. Yeah.
And the second question, the granulate that you feed with this CO2, if it was just left in nature, how long would the same process take? Do you have any estimations of that?
Well, I cannot exactly say what the equivalent is, but basically, if you take concrete today, carbonation always takes place. So if you would take 1 ton of gravel, the problem is that you would have to, in order to get an uptake potential of come down to several months, you would have to spread it very, very thin across a huge surface area, because usually that gravel is stored into large piles, and then the carbonatization cannot take place in that time.
Thank you.
Maybe I missed it, but I had a question about, for each ton of concrete recycled, how many CO2 can you store?
You didn't miss it. Yeah, no, I didn't mention it. Well, so a typical number is for each ton of recycled granulates, you can store about 10 kilograms of CO2. Now, this can change heavily because it depends on the size of the granulate. If we carbonate sand, it can go up to 25 kilograms. If we carbonate huge stones, it can be 5 kilograms. But what we can basically, another conversion is if you take a medium-sized concrete recycling company, they have about 100,000 ton per year, and they can store between 1,000 to 2,000 ton per year.
So they play on the volume.
We pay them on the volume. Absolutely. Yeah.
Thank you.
Thank you for your presentation. The average of the price you can pay for the liquefied CO2 from the biogas plant, how could it be, more or less, for your business plan?
You mean how high it is, or what the price is that we can pay for the liquefied gas?
Yeah.
Well, that obviously depends a lot on the energy mix that has to be used to liquefy the gas. So and what the current stage of the energy prices are. At the moment, in average we pay somewhere like 80 euros per ton of liquid CO2.
Mm-hmm. Okay, 80 euros per ton.
80.
Yeah.
Yeah.
Okay, and you are responsible of the logistic, or you are asking the biogas plant to make it?
No, so we are responsible for the logistics. I mean, what we found when we started to build up the business model is that if you try to work with an existing gas logistic company, they are afraid of transporting not clean CO2 that is not as clean as it is that we use it. So therefore, we are starting to build up our own logistics as well. So we have own ISO containers, and we basically drive as well the logistic component of the value chain. Yeah.
Thank you.
Thank you, Michael. Thank you. Donc, on va passer maintenant au prochain intervenant. Et nous allons découvrir la vue d'un autre monde, on peut dire presque un autre monde, où un monde où les bétons est fabriqué par des algues. Les algues qui sont utilisées pour cultiver un biocomposite qui a les qualités d'un béton, mais sans les carbones.
A new composite that is used to develop it without carbon. So I'm going to welcome Loren Burnett from Prometheus Materials from USA to take the floor. You're welcome.
Good afternoon, everyone. I'm Loren Burnett, President and CEO of Prometheus Materials. So we are focused on concrete. Concrete, as you know, is huge and a huge problem from a climate perspective. As stated earlier, there's about 7 to 8% of global CO2 emissions are associated with the production of cement and concrete. Also, the production of concrete consumes about 9% of water production on an annual basis. And also, of course, it's the second most used material on Earth, second only to water. So the problem we're dealing with here is very large and very, very dirty from a climate perspective. But it's actually worse than this. Because over the next 37 years, global stock of space is forecasted to double. That's the equivalent of building a new New York City every month for the next 37 years. So think about the amount of concrete associated with this. Enormous problem. So we are using biology. We're using algae and stimulating a process called biomineralization, which I'll talk about on the next slide. We're mixing that with aggregate and some other things to create an ultra low carbon alternative material to concrete. We are not concrete. We are not Portland cement. We are a completely different material with similar characteristics. And that's a really important thing to keep in mind. So biomineralization, it's using biology to create minerals. In our case, it's calcium carbonate. So what we are doing is we are stimulating algae to create biomineralization on a commercially viable time scale. It's a very similar process to what nature goes through to create coral reefs and seashells. It's biomineralization. So it's been around for a long, long time. So basically, we are just stimulating that to be to our benefit on a commercial basis. So the way that we are different than concrete from a CO2 perspective is we do two things. We avoid and we sequester. So from an avoidance perspective, if you look at the way the cement is made, in particular, they mine limestone, they truck heavy limestone using fossil fuels to the cement plant. They then superheat that cement, that limestone in industrial kilns using fossil fuels to do so. And by the way, once they superheat it, limestone does what? It releases CO2. They then transport that heavy cement to a local concrete plant, burning more fossil fuels and CO2. We avoid all of that stuff. We don't do any of those things whatsoever. So our process is completely different. Again, it's using algae, and everything we do is at ambient temperature, ambient pressure, nothing superheated, no fossil fuels used whatsoever. So that's the avoidance side. And then we sequester. So the way we sequester CO2 is because we are, again, using algae, and that algae goes through a photosynthesis process. So it naturally sequesters carbon. And then the biomineralized calcium carbonate. Both the algae and the biomineralized calcium carbonate are then sequestered into our long-term building materials. So we avoid and we sequester. So to give you a little bit of background, the technology was started by 4 professors at the University of Colorado. They entered into a research agreement with the U.S. Department of Defense. Basically, what the Defense Department was looking to do was they wanted to be able to create force protection structures in the middle of resource-deprived environments, which is Department of Defense speak for the desert. And so they knew they couldn't fly in concrete, and they knew they didn't want to truck it over hostile territory. So what they wanted to see if they could use living materials such as algae to produce some sort of material that could be used for force protection. That was successful. We formed the company. I joined the company and formed the company back in March of 2021. We then entered into an agreement with Microsoft, the folks that are building their data centers all over the world, to prove the technology and to do additional testing, which was also very successful. We closed our Series A funding with Sofinnova Partners out of Paris last March. And as of a week and a half ago, we received our ASTM certification on January 31st for both structural as well as non-structural applications of CMUs, load-bearing and non-load-bearing. So we're very excited about that new news. In fact, a press release just went out yesterday. So in addition to Sofinnova, we have some world-class partners that have become investors in the company that are experts in the use of concrete. So Microsoft, I mentioned, we went through the project with them. They became an investor. The Climate Innovation Fund is the investor, but our real partner is the organization that's building 50 to 100 data centers worldwide on an annual basis. GAF Roofing and their sister company in Europe, BMI, together represent the largest roofing materials company in the world. SOM, Skidmore, Owens and Merrill, the architectural firm that designed the world's tallest building, the Burj Khalifa over in Dubai, as well as One World Trade Center in New York, and then Autodesk Foundation. So what you see with Microsoft, GAF, BMI, and SOM is you've got three organizations that either specify or use large amounts of cement and concrete. And they know that that's not sustainable. So all three of those organizations actually came to us to help them reduce their CO2 profile. And so we're working with all of those, and they liked what we're doing so much that they all invested in our Series A. So how are we different than cement and Portland cement and Portland cement-based concrete? So from an embodied carbon standpoint, we reduce embodied carbon by about 90%. Now that we've gotten our ASTM certification, we'll begin the LCA process. But we think conservatively 70 to 90%. I think it's very likely that it's more in the 90% range. From a curing process, we cure over a 7-day period, where concrete is typically considered to be curing over a 28-day period. Our compressive strength is right in line with what's required for concrete masonry units, which is what we're initially producing at about 2,400 PSI. What's really interesting here is on the flexural strength. Concrete is typically considered to have about a flexural strength of about 250 PSI. Early testing on our product has us at 2,500, so an order of magnitude higher than what you see with concrete. And also, we mentioned that the concrete uses 9% of industrial water. We go through, our curing process is dehydration. And so we basically return virtually all of the water used in our process back to the atmosphere. And we have about a 15% weight reduction as compared to concrete. Also, from a thermal conductivity, there's almost an R value associated with what we have. We have about 10% of the thermal conductivity of traditional concrete, which is also something that's really exciting for us. So our go-to-market is we're producing CMUs, concrete masonry units. Don't think of us as a concrete block company. That's just our first unit, our first production. But we will be producing additional precast items very, very shortly. And we're focused on the demand side. We believe that the way that you change this industry is by getting the companies that specify or use large amounts of concrete to specify to the concrete industry what they want used. So this is our midterm vision. We mentioned other precast concrete products, which you'll see here. This is just a representative sample. There's literally thousands from which to choose. And then ultimately getting to a ready mix application within about the next 24 months. And then our long-term vision is consistent with both Microsoft's as well as SOM's, which is that we are focused on reducing CO2 by a gigaton a year. We know we're not going to do that by ourselves. We know we're not going to do it next year. It's going to be through a licensing model where we will be licensing our technology to large producers and distributors of concrete, cement, and precast concrete products. And ultimately, we are in accordance with the SOM Urban Sequoia idea, which is where basically buildings in cities are living and breathing things that convert CO2 back to oxygen and sequester carbon. We've had a lot of press that we've been fortunate enough to have a lot of press and a lot of excitement about what we're doing. And we're very excited about what we're doing. I'd be remiss to not mention that we are starting our Series B process. So if there are any investors that are interested in talking to me about Series B, I'd be delighted to chat. Thank you very much.
How's the availability of the raw material that you need next to LG?
I'm sorry?
How's the availability of raw material that you need next to LG?
So so we are producing the algae ourselves, by the way, right now in photobioreactors. So the algae we use reproduces itself in every 4 to 6 hours. So it's very, very productive from that perspective. The other materials are very, very available as well. And then, ultimately we're mixing sand and aggregate in. Our desire is to replace sand at some point with some sort of alternative aggregate. Whether it's recycled glass, recycled mirror, or a host of other things.
Hi, thank you for the presentation. It looks impressive, the characteristics of the material. So one question is, what are the downsides of it? If it has so good compression, also flexural capacity, that's incredible. So what's the bad points of the material? And then are you producing it just in the US, or are you planning to produce this material in Europe or other places in the world?
Yes. So to answer your second question first, we will be beginning early production now that we've gotten the ASTM certification. We didn't want to produce anything until we knew that it was certified. Now that it is, we'll begin a pilot production, which is fairly small scale production. You're not going to build a data center with that. Our use of proceeds, one of our use of proceeds for Series B is to build a scale production plant where we'll have 4 production lines that will produce 4 different precast products. The reason I'm here and now is because we definitely have plans to also begin production over in Europe. So we have, again, we've got with Sofinnova Partners, our European-based, our Paris-based investor. We're very interested in coming over here as well.
Hello. I saw you at fiber. How much do you use in your product, or how much you intend to use?
In terms of fiber, I can't give you a percentage, but it's a fairly low amount. But what's interesting about the fiber, that's a great question, is that different than what you can do with concrete. We can come with concrete. You can put about 3% fiber mix in, and with our product, we can get up to in excess of 10%. So there's an opportunity to mix different types of fibers in at a much higher level. Our goal overall, we haven't begun testing of this yet, but our goal overall would be to be able to use certain types of fibers in enough quantity that we could actually eliminate the use of steel rebar in certain applications.
Thank you.
Yeah, my question related also to fiber. Is it these numbers of the flexural strengths? Is it including the fiber that is in the mix?
Yes. Yeah. Yes. Everything we're doing right now has the fiber in it.
Yeah, and it's only hemp fiber you work with, or are you trying other?
We're trying other ones. The hemp is what we're using substantially at this point, but we're always trying other fibers, and we're very interested in using other types of things that might of products that can embody carbon or that can sequester carbon. Even the production from air capture plants. We would love to at some point get our hands on that solid fiber that comes from those and potentially incorporate that into our product.
Je peux poser la question?
Hi.
Hi, good morning. You didn't mention how much of algae do you need to make, let's say, 1 kilogram of your mineral calcium carbonate, and how long does it take them to prepare this quantity? Just to have an idea on the time scale and the volume of algae you need to produce.
So the volume of algae is that's something that's confidential at this point. But I can tell you that the production process of the algae, it's actually very quick. So we can, again, it reproduces every 4 to 6 hours. We're doing that in our plant and photobioreactors. The time from harvesting the algae and the calcium carbonate, the biomineralization, to the time we actually put it into our mix can be a matter of hours. It's very quick.
Thank you.
Thank you very much. Thank you.
Thank you, Loren. Thank you. Donc maintenant, on va voyager avec les biochars, qui est également un sujet d'actualité qui se développe comme un matériel très intéressant dans les domaines du bâtiment.
Topic regarding innovative materials in the building construction. So I would like to welcome now Venna von LEPEL to the microphone, please. It seems like our next presenter is not here. Well, I'm not sure our next presenter is here. Let us hear. We hope that Gaspar will welcome us later on, but let us welcome now Julia Hort, who will be introducing the feedback of CarStor technology from Germany, and who will also speak to us about biochar. So we are still within the same topic. Let us enjoy it.
Thank you. So, question to you first.
Merci beaucoup.
Do
J'aimerais
we want to build
avant tout
construction
vous poser
materials or buildings which are just less bad, or do we actually want to embody carbon? Do we want to integrate a negative technology into the buildings? My name is Julia ROTH. I'm from CarStorCon. This is what we do. We transform construction materials, concrete in this case, into carbon things through the use of biochar. So let's see. It works. Actually, you stole my example. The demand of construction materials is huge. As mentioned, we will need to build the city of New York every month for the next 40 years. So vast quantities. And it's usually seen really as a problem because, as we also saw, the numbers are quite alarming of the CO2 impact that it has. But maybe just for this, for the moment, you can maybe see those sheer amounts of material which are used and which are moved. They also hold a great potential of actually storing carbon in them. It is a material which is already handled manually through industrial processes. So adding a negative emission technology is actually quite a good thing to go to. So it's quite clear where the goal is set. The question is how can we do that with other materials that we saw? But if we stay with the concrete, which is going to be at least for the intermediate time, the material that will stay, that is also used and will be used in the next years vastly. Maybe for all of you who are not so familiar, we have heard a lot of cement and concrete. What's actually what is it? So concrete is a mixture of cement and water and aggregates and some additives usually. And the problem is the cement and the production. So if you have 1 ton of cement which is produced, you usually have 0.6 tons of CO2 which are just emitted just by the process of generating this material. And now we can change change the materials that we use. For example, use alternative binders, not cement, or use fly ash. This is quite common already, or use some of the pre-speakers solutions. But of course, we can also use biochar as a derived negative emission technology to reduce actually the carbon footprint. This has maybe also a positive side effect in terms of resource depletion. It has been more in the media lately. The use of sand is becoming quite alarming. We have a lot of problems because also the sand is becoming scarce, and we see that a certain fraction, especially the fine particle fraction, can be substituted with biochar. So I'm sure you're aware biochar as being one of the negative emission technologies which are on the IPCC report. The question is it also interesting for the construction industry, being negative emission technology? Yes, of course it is. It is scalable. It is already today the biggest CO2 removing technology which is there. So it's big quantities, is scalable. So of course it is a good idea. Also for the biochar side, it can maybe mitigate a bit one of the problems that biochar always faces, where it's seen as not being so permanent, because we see what happens actually if you put the biochar into cementitious matrix. It actually really is integrated in the mineral structure, therefore very, very high durability, even over several recycling cycles can be ensured. But of course, there are some hurdles, otherwise it would have already been there. As you can see, the chemical and the physical properties of the char are not like any material which is used today, like also fly ash or any other material is just from its properties, it's different than the biochar that we currently see. Also, biochar is, let's say, the construction material that is used today is very homogeneous. So this is a prerequisite that the construction material has, or the construction material industry has, with the handling today. And for those of you that know biochar, it is a lot. It has very cool properties, but it's not homogeneous. So those are two of the main factors. And of course, if we look at construction materials in general, not only the concrete, which is the focus here, but we see that we have very different prerequisites of the material, of how it works in the construction material to make it a good product. So it really depends on where you want to put it. You need different properties. How can we, what are we doing now? Like how can we mitigate those problems? For the first solution is what we saw is to really have a good control over the factors throughout the whole production process. So really ranging from the biochar over the production of the biochar, of the after treatment process, to really control every factor of those steps to have and to optimize it to that you have a functionalized product that you can then use. Or you have basically an after step where you homogenize the product so that it can be used and kind of like tame out the different qualities that you have. How does that look in practice? We developed a specialized biochar, specialized treatment process and production process, which then can be used in construction materials. We see a couple examples here on the right side. We call it Climate Edge. It is you can put the material just into the concrete, so can be integrated into the currently in the current processes quite well. And for us, it was very, very important, and not only to have this carbon sequestration potential, but and I want to explain this here on the graphic. One of the main points is really improving a functionality of the concrete. Otherwise, an economically viable case is just going to be difficult, but to reach it just by the storing potential. So what we see here, of course, is a carbon footprint reference. Then on the next, the little one there is we actually managed to tune the biochar in a way that you can reduce the cement that you are using for the concrete quite significantly, and even though reducing it, reach same compressive strength and flexible strength, and even improve it depending a bit on the type of concrete. Then yeah, if you don't use it. So the next thing is the recarbonization. So we're hoping Neustark is really pulling off their business model quite well, because then, of course, also this is helping the global footprint of the CO2 for the concrete. And then we add our climate add, which is, of course, having the storage function. It has been from material that has been removed from the cycle, and therefore we can actually come to a climate positive footprint. Summing this up, what can be the benefits of the biochar? Of course, durability, as I mentioned, it can be stored over multiple cycles, even after recycling. The bonds which are formed keep the biochar, because it's inert material. Keep it quite strong in the matrix. Is additionality. So of course we can use it in combination with other CO2 sequestering or CO2 reducing factors, like using different materials or binders or anything. The material features, which I try to point out, is one of the most important things to really have a technical benefit of using the biochar into concrete. And then, of course, the local value chains are one of the main points for the construction industry. It is an industry which works quite locally. We have the facilities quite locally, and biochar, as we all know, can also be produced and used locally. Maybe how does that look in practice? We hear some reference projects from from last year. We have, for example, here on the left side, it's a family home that we built. We have an office building which was built. So we're like trying to take here some examples which are a bit across the different sectors. We have a technical building which is actually an infrastructure, like a public infrastructure project, which was very interesting and very good that we were able to do this, as well as a more industrial big sites or big scale application, which is a wood, gas and saw workshop that we are currently building with our material. You can see the carbon storing functions here. So we are really in scale up, and we're looking really much towards this coming year, and storing away lots of tons. Thank you so much. We wouldn't have come that far without our partners. Here maybe some of the reference. Some you can also see or have also some talks. Oh, sorry. And that's it. Thank you. Any questions? Okay, then thank you so much. Sorry.
Hello, what's the maximum concentration of biochar that you can put in the cement by mass?
Mm-hmm.
And what is the thing that determines that maximum?
Mm-hmm.
What's the pinch point?
Mm-hmm. So we have so far used up to 30 mass percent. This is, I know this is quite a lot. The second question is, so it depends always a bit on the use case. It depends on the material where you put it into, and it depends highly on the process you treat the char with before putting it into the concrete. So we have certain applications where you have a bit reduced. There you go up more like up to 20% or 15%, which is treated a bit less. If you treat it differently and treat it more, you can actually increase it quite a lot. But if you can also talk afterwards, but yeah. Thank you. Oh, sorry. Now the questions come. Yeah.
So thank you very much for the and quite interesting. I had two questions. The first one is on your slide, maybe 8, you have mentioned that you have also improved properties, functional properties. I wanted to know what you are having in mind when you mentioned that. And the second one is I've seen that you have had some interesting projects in delivering the concrete or the eventual material to real sites productions. How did you handle the standards to use the concrete eventually for real job sites? Thank you.
Sorry, can you say the first question again?
So the first question is regarding the functional. So you have mentioned that you have functional properties.
Yeah, exactly. So what we saw that, for example, the compressive strength and the flexural strength are both improved. This is definitely, and also in the quantities that we have seen or we researched and put, is definitely not the case for all the biochars. In most cases, biochars will not have this effect. It is really the one that we found here and tuned, which was able to really show in those improved properties. Sorry, my mind is, the second question was
the second question is regarding the job sites that you have conducted. So I imagine that you had to go through proving the durability. I mean, how about standards and accepting these novel types of materials?
It is a bit different depending on the country. So Germany or origin actually is a bit more difficult. So in Germany, you have very high restriction processes on the to have a general admission. So to really move forward, we focus on, as well as the projects that we show here, on let's say you kind of get an approval for the one site. You show that like all the required technical parameters. We always accompany with a lab with external validation on site as well. And of course the concrete manufacturer and all the parties involved. So we accompany this through the whole process. But so far we have, let's say, like site-based admission. And because the general admission in construction industry, it's quite lengthy. We're applying, but it's until we have that, we do it like base by base. Thank you, and thanks for repetition. Okay, thank you.
Merci Julia. Donc, on va terminer cette première matinée sur ces sujets qui restent quand même passionnants. Je remercie tous les intervenants les intervenants qui ont participé.
That was very exciting. I would like to thank every participant who has joined us this morning, and I thank you all for joining us for this first session, the morning session. And we will be meeting again at 2 p.m. to speak of defossilizing construction materials. So excellent, bon appétit, enjoy your lunch, and catch you later.